We are looking at the knowledge area chemical change. Right, let's look at this aspect of solubility of ionic substances. Right, we're looking at solubility of ionic substances. Here we have a periodic table, right? So let's revise some of the group names. We know that this group is alkali metals. Group 2 is alkali earth metals, right? And then we have group 7, which is halogens. Okay? And if we have these groups, any of these metals reacting with the halogens, we get halides. Right. So if we look at group 1 and group 2 metals, we find that when they react with halogens, we get halides, and these halides are soluble. Okay? They are soluble in water. Right, we only interested in its solubility in water. Then let's look at some others. Here we have, for instance, silver, right? Here we have mercury. Here we have lead, right? These here we have that, and even that, when it combines with the halogen, we get halides, right? So silver, maybe with chlorine will be silver chloride, mercury with bromine will be mercury bromide, and these halides are insoluble in water. Insoluble, right? In water. So they insoluble in water. Okay. Just gives you an idea. So you have that. Now let's just go and have a look at some of the rules here. We've got soluble compounds, right? And we've got several anions. We've got nitrate, so compounds containing nitrate, right? All are soluble, and there are no exceptions, right? So you got important exceptions, and here we don't have any exceptions. That means all compounds of nitrate are soluble. So it could be calcium nitrate, magnesium nitrate, aluminium nitrate, silver nitrate, any nitrate, right? Combining with any positive ion, it's soluble. Then we have acetates. Okay? Acetates are also soluble. Acetates are also soluble, right? All of them, irrespective with which cation they combine. Let's look at the halogens, right? And I showed you where they are in a periodic table. So that's our halogens. Chlorine, bromine, iodine. When they form ions, then we refer to them as chloride, bromide, and iodide, right? And these are all soluble except for silver, mercury, and lead. So all chlorides, sodium chloride, magnesium chloride, aluminum chloride, they all soluble. But silver chloride is insoluble, mercury chloride is insoluble, and lead chloride is insoluble. The same thing goes with bromide, right? That's insoluble. That's insoluble. And lead bromide is insoluble. And iodides. So, silver, mercury, and lead, right? These are the halides that are insoluble. That means they don't dissolve in water. If you look at sulfates now, all sulfates, most of the sulfates are soluble. The only ones that are not soluble is Sr, which is strontium, barium, mercury, and lead sulfate. So these are not soluble. Okay, so if we have a look at it, here we'll see, for instance, here's barium, right? There's strontium, right? And those sulfates are not soluble. Okay. Then we have our sulfides. So that's our sulfide. Here we find that most of them are insoluble, but the ones that are soluble is ammonium sulfide and alkali metal cations, right? And together with calcium, strontium, and barium. Right, now I showed you where the alkali metals are. So that means all alkali metals of sulfide are soluble. Okay, all others besides them are insoluble. Then we have carbonates. So carbonates are generally insoluble. The only soluble ones are ammonium carbonate and alkali metal cations, that combine with carbonate and iron, they are soluble. Otherwise, the rest is insoluble. Okay. So, let's look at the solubility rules. The solubility rules for ionic substances. So here we have, this is a solubility guideline. In determining whether or not ionic compounds will be soluble in water. Okay. And the solubility of a substance is the amount that dissolves, or the amount of solute that dissolves in a quantity of solvent. That gives you an indication of solubility. Now, guidelines for some common ionic compounds. Okay, we got some guidelines here. So what we do know is we have soluble ionic compounds, right? Like I've just drawn your attention to, and the soluble ionic compounds are referred to as electrolytes. Right, what does that mean? When these ionic compounds dissolve in water, they form ions in solution. Right, we've dealt with that in our previous lessons. And then if we have an insoluble ionic substance, we find that it's a non-electrolyte since it has no ions in solution. So you can have an ionic substance, many of them are soluble in water, right? But there are some that are not soluble in water. Now let's just review that slightly. Here we got substances that are soluble, a substance that is soluble in water, and it's called an electrolyte. So we have seen this in previous videos. We got sodium chloride, right? And sodium chloride is made of sodium ions and chloride ions, right? Sodium ions and chloride ions. But what we know that sodium chloride dissolves in water, and here's a microscopic description. What then happens is that the chloride ion gets hydrated with water molecules, and uh, sodium ion gets hydrated with water molecules around it, and since these ions are hydrated, we find that the ionic substance can dissolve in water. So this dissolution or dissolving is energetically favorable. Remember that to break the ions, you need energy, right? Energy needs to be provided in order to separate the ions in a crystal lattice. But then, when these ions separate, we find that the water molecules surround it, and the water molecules that surround the ion becomes hydrated, and that process releases energy. So the net effect for this dissolution is energetically favorable, right? But you will deal with the issue of enthalpy in grade 11. Okay, so here what we have is essentially we've got sodium chloride. So we got sodium chloride like that, which was our solid. Okay. And then we had water, and we see that we have Na plus and aqueous indicating that it's hydrated, right? Plus Cl minus, and that's hydrated, right? So since it dissolves, we find that we have ions in solution. We can also write it like this: NaCl aqueous, right? Then I don't write the water there, and that implies that it's in a water solution, right? And it forms ions in solution, so it's an electrolyte, right? So all ionic substances that are soluble in water, we can then dissociate the substance into its ions like that. So that's one way of writing it, or we could write it like that. Let's look at the next one. Here we've got silver chloride, as you can see, right? We've got silver chloride here, and here you got these water molecules as well. But in this case, the forces between the chloride and the silver ions are strong. They're very strong, and what happens is these polar water molecules cannot break down or separate these ions because the forces are relatively strong, right? And then the process of dissolving is not energetically favorable, so it doesn't silver chloride doesn't dissolve. I've just got its properties here, but let's look at this particular property, solubility. As you can see, the solubility of water is 520 micrograms per 100 grams at 50 degrees Celsius. So which essentially tells us that it's insoluble, right? It's very, very slightly soluble, but for our purposes, we categorize it as being insoluble. Okay? Which means here AgCl, it's like the solubility is 20 micrograms, which is 520 times 10 to the minus 6 grams, right, per 100 grams of water, which means it's practically insoluble, right? And we categorize it as insoluble because its solubility is very, very low. Now, in this particular case, you don't have ions in solution. So if we write this now, AgCl solid, right? AgCl solid, okay, AgCl solid, and if we say we add water to it, what happens? It remains the same, AgCl solid. Nothing happens, it does not dissolve, okay? And as you can see, I've said it's a solid, I've added to water, it remains a solid, so it is insoluble in water. It could be soluble in some other substance. As you can see here, it's soluble in ammonia, it's soluble in HCl, H2SO4, in cyanide, but we're not interested in its solubility, of its solubility in other solvents. We're just looking at aqueous solutions. Right, now, equations when ionic substances dissolve or does not dissolve in water. Okay, I have shown you here, I've alluded to that, but let's just look at it. Example, all nitrates are soluble, right? And some halides are soluble. Okay, I showed you that when we looked at the periodic table. So let's say, for instance, let's look at a nitrate that is soluble. So if we look at, for instance, okay, all nitrates are soluble, so we can take any nitrate and we could say, okay, let's say we have potassium nitrate, okay, which is a solid, and which we can then say H2O, and that will give us K plus aqueous plus NO3 minus aqueous. That's one way of writing it. Or alternatively, we can just write it without the water and say aqueous, which means it's dissolved in water, and that gives us K plus NO3 minus. Okay, so all nitrates are soluble. Whichever nitrate we have, it can be soluble. Let's maybe take another example. Let's say, for instance, we want to take another one, BaNO3, that's barium nitrate, right? And if that is soluble, right, how do we separate it into its ions? We know that Ba has a charge of 2 plus, so that's aqueous. And then we have nitrate, which has a charge of -1, and that's aqueous as well. But we need to have a charge balance, so we need to have. So for every barium ion, we got 2 nitrate ions, so we know that the charges balance. Okay? Then we got some halides that are also soluble. So which are soluble, we looked at that, and I showed you that group 1, when it reacts with a halogen, the halides are soluble. So let's take a halide halogen and combine it with group 1 metal. So we could, for instance, say, all right, let's say we want to take potassium, right, and combined with bromine, so that is soluble. Okay, alright, so that's soluble, and we say, alright, K plus aqueous plus Br minus aqueous. So whenever it's soluble, we can break it up into its ions. Right. Okay. So there you have that. Right. Now let's look at examples of insoluble ionic salts. So some halides are insoluble. Okay. And which halides are insoluble? We saw here. There we see the silver. If we look at this here, say chloride, then we see silver chloride is insoluble, mercury chloride is insoluble, lead chloride is insoluble. Isn't it so? So you go to the table and you see which of these are insoluble. So if we say AgCl, right, it's our salt, and in this case we say H2O, we still get AgCl solid, since these are insoluble ones. So AgCl is insoluble. Okay, and you look at our sulfates now, right? And if we go and have a look at our sulfates, which sulfates are insoluble, right? Here you got your sulfate. If you look at your sulfate here, which of them are insoluble? The barium sulfate is on, strontium sulfate, and lead sulfate. They are all insoluble. Okay. So, in terms of our sulfates, if you look at our sulfates, so we say barium sulfate. So we got barium sulfate. Okay. Barium sulfate is insoluble. If I say H2O, here we find that it doesn't dissolve, so these are insoluble. Okay. Then if we look at now carbonates also, we find that which carbonates are insoluble? There we have it. The carbonates that are insoluble, the only carbonates that are soluble is ammonium carbonate and alkali metal carbonates. Otherwise, the rest are insoluble. Okay? So, which means, in that case, we got barium carbonate. Okay? Barium carbonate, solid. And if we add it to water, we find that it's insoluble. BaCO3 solid. Right, so these are all insoluble solid. That's an insoluble halide, that's an insoluble sulfate, and that's an insoluble carbonate. Right, now let's look at some molecular substances. We're dealing with ionic substances, but we need to look at some molecular substances basically because some of them are electrolytes. So if we look at soluble in water, but it's non-electrolyte. So it doesn't mean if something is soluble in water it's an electrolyte. It's only an electrolyte if it has ions in solution. And then we look at soluble in water, and it is in water and it's an electrolyte. Okay. And then you can also have some that are insoluble in water and non-electrolytes. Let's look at the first one here. So here we could have, for instance, sugar, which is that, an O6, and if it's soluble in water, so we say aqueous. Alright, let's maybe just do this. If we do that and we have a solid, right, and if I dissolve it in water, then we have C6H12O6 aqueous, right? Doesn't form ions, but it dissolves in water. And if we have, for instance, CH3OH, which is methanol, we know, and if we add water to it, it becomes CH3OH aqueous, right? It also dissolves in water, but it doesn't form any ions, right? Now, and these are molecular substances, okay? So they non-electrolytes. But let's look at some different molecular substances, like an acid. An acid, we find that if we have HCl, right, and in water, what happens is it has no ions in that molecule, but in water it can form ions, and it forms H plus ions plus Cl minus ions, right? And you'll learn more about that in grade 11, but here I'm just giving you an indication that when an acid dissolves in water, it forms ions, right? And when you look at this here, you'll see, firstly, how do you recognize an acid? I have spoken about that in previous videos. HCl, when you see a H, right, it gives you an indication that you are dealing with an acid. HNO3, these are all molecular substances. So here now, even if we have HNO3, okay, say a liquid here, and that gives us in water, it then gives us H plus aqueous, right? H plus aqueous plus NO3 minus aqueous. Alright, so, or perhaps let me just write it this way. So we say aqueous. Right, so when an acid dissolves in water, it breaks up into its ions. Now, normally in solution, H plus right, exists as H3O plus. This is known as the hydronium ion. All right, we'll deal with that. You'll deal with that when you get to grade 11. So for now, know that when a molecular substance like an acid dissolves in water, when it dissolves in water, right, it forms H plus ions and chloride ions, right? Although the H plus ion in solution, it exists as a hydronium ion. And that's important next year when we're going to talk about acid-base reactions, and more can be said about it next year. Here we've got another molecular substance, NH3. Alright, so if we look at NH3 again, NH3, and again say it's in a water environment, right? Okay. And there's normally a gas, and which will then give us NH4 aqueous plus OH minus aqueous. Right, so here we have the gas dissolving water. You'll notice I haven't balanced that reaction. I'm just giving you an indication in a water environment what ions are formed when ammonia dissolves in water, right? And we know that it forms an electrolyte because it conducts an electrical current. Okay, so that here it's an important base that you're going to be dealing with in grade 11, and these and I've mentioned two of the acids. Okay. Now let's look at soluble salts of nitrates. Here we have them. We've got sodium nitrate, potassium nitrate, barium nitrate, calcium nitrate, and magnesium nitrate. All these are all soluble salts, right? Which would mean if I take, for instance, NaNO3, right? I take NaNO3 and we dissolve it in water, right? I could put that, or I could write it, I could put water on the arrow, or I could write it like this: Na plus NO3 minus aqueous. Okay? If I take now maybe KNO3 is also soluble, so KNO3 is a solid, and when it dissolves in water we say K plus aqueous, meaning that it forms ions in solution. Right. And then if we look at it, we can take maybe calcium nitrate there and see how that breaks up. So we say CaNO3, we know that salt, and if it's dissolved in water, what happens? We get Ca2 plus, right, aqueous, plus 2NO3 minus aqueous. Right, and again I'm balancing the charges. Okay, so those are all soluble nitrates. Okay, and all nitrates are soluble, like I've said. Even if we have silver nitrate, that is also going to be soluble, right? All nitrates are soluble. So let's say, for instance, we have AgNO3, right? Halides of silver are not soluble, but the nitrate is. So Ag plus aqueous plus NO3 minus aqueous, right? So all nitrates are soluble irrespective with which cation they combine. Now, insoluble salts of halides. Here we have insoluble salts of halide. Here's a silver nitrate. Why I've got it here? Because it's actually used to test if we have a halide in solution. But here we've got insoluble halides. So AgIs is insoluble, right? AgBr is insoluble. AgCl is insoluble. Right, so you recognize these are insoluble, so they in actual fact form precipitate, something that doesn't dissolve in solution. And you'll see, how do you recognize a silver iodide? Is slightly yellow in color, right? If you look at silver bromide, it's like white to pinky, to white to creamish. And then you see silver chloride, right? It's but whitish in the precipitate. So it's but the bromide and the chlorides, but difficult to distinguish. But we see that they form precipitates, right? So silver chloride, AgBr and AgI are insoluble in water. We know that all other halides, like for instance alkali metal halides, they are soluble. These are insoluble in water. Then here we have insoluble barium sulfate, right? Here's barium. When you dissolve it in water, you find that it doesn't dissolve in water. So if you have, for instance, BaSO4 and we add water to it, what happens? We still have BaSO4 solid. Alright, so it doesn't dissolve. There's no ions that are in solution, and so it's a non-electrolyte. Let's look at barium carbonate. Barium carbonate also insoluble in water. Okay, so if we have here barium carbonate, which is a solid, and in water, what happens? It doesn't dissolve, right? It does not dissolve. Okay, so B does not dissolve. Same thing. So these are insoluble. Barium carbonate is insoluble, and barium sulfate is insoluble. But you'll notice that barium carbonate precipitate looks very similar to barium sulfate precipitate here. Why I'm drawing your attention to this is as we carry on, we will need to distinguish between the two precipitates. Right, now if we look at chemical equations, right, can be written to show whether the dissolved substances present are predominantly ions or molecules. And when the complete chemical formula of all reactants and products are used, the equation is called a molecular equation. Right, and a complete ionic equation shows all dissolved strong electrolytes as their component ions. Right, and then the net ionic equation, those ions that go through the reaction unchanged, we call them the spectator ions. They are omitted. Okay, so here in this section, we're not going to look at the net ionic equation, right? But we're going to look at the ionic equation, but not the net ionic equation. That will be dealt with in the next section. All right. So now let's look at precipitation reactions. A precipitation reaction are those in which an insoluble product called a precipitate is formed. Reactions in which positive ions and negative ions appear to change partners conform to this general equation. Right, in a precipitation reaction, it looks like the positive ions and negative ions appear to change partners. Now let's look at this here. The general thing is you got, say, AX plus BY gives us AY plus BX. Right, which means if you look at here, you have, for instance, take that and take that, right? And here your A, and in potassium iodide, your A refers to K. And here in this one, you got B, which refers to Ag. Right. So what happens here is you'll see that K and the anion related to K is I, negative. Here you got Ag and the anion related to that is the nitrate ion. So what in essence happened is the K plus exchanges with the Ag, and the Ag exchanges with the Ki. So when that happens, you'll see Ki's partner was I negative, right? But what has happened, and Ag's partner is the nitrate anion. But because here you have the partners exchanging, which means K plus now combines with KNO3, as we show you there, and we find that AgI changes its partner, and the partner is then iodide, like that. Okay, so if you look at this, the anions of the respective cations have changed, right? And when you see this, you find that this is soluble, that is soluble, that is soluble, and this here is insoluble. So a precipitate has formed in solution. So whenever we find that a precipitate can form in solution, we find that it actually drives that particular reaction, right? It drives the reaction. Right, so once we get a precipitate forming, we find that that particular reaction is driven by the formation of that precipitate. Right, now let's look at the test for ions. We're going to look at how do we test for chloride ions, how do we test for sulfate ions, and how do we test for carbonate ions. So first thing we need to do is identify the ions from a description of the reactants mixed. So for instance, if I am dealing with potassium iodide, I need to identify the ions. The ions would be then K plus and I negative. And we also need to observe the products. Right. Right, now let's illustrate the formation of a precipitate. Okay. We have a potassium iodide solution mixed with a lead nitrate solution. Okay. Here we have potassium iodide, right, solution, and we're mixing it with a lead nitrate solution. As soon as we see potassium iodide is added to lead nitrate, so here we have potassium iodide, right? And it is poured into a solution of lead nitrate. What do we see? We see a yellow precipitate, right? A yellow precipitate. Right, and here you see the precipitate settling at the bottom, and that's insoluble in water. But let's just look at a microscopic description of it. And here we got lead nitrate, so there you got your lead ions and you got your nitrate ions in solution, right? So both are electrolytes. What then happens is the potassium changes its partner, and we find that we get potassium and nitrate joining up, and then lead and iodide. So here you see your precipitate. Okay, here's your precipitate forming here. All right, so we need to see how we look at this. What we need to do is we want to predict the identity of the precipitate that forms when solutions are mixed, and we want to write a balanced chemical equation for this, right, or a molecular equation for this. So this is what we do. Okay, so how do we go about doing that? So we have two ionic reactants given, and we are asked to predict the insoluble product that they form. Okay, and then what we need to do is consider the ions present in the reactant and exchange the anions between the two cations, right? And we need to write a chemical formula for the products and determine which is insoluble in water. So if we look at the reactants now, what do we see? We have lead, nitrate, potassium, and iodide ions, and if we exchange the N ions, we will get PbI 2, and KNO3. And we know that KNO3 is soluble and PbI2 is insoluble, right? And then what we need to do is also show the phases that we have here. Okay, now let me illustrate all that. So we say, all right, we got potassium iodide, correct? And it's in aqueous solution, which means it's soluble. So what do we have? We have K plus ions, correct? Plus we have I negative ions, right? And then we have lead nitrate, which is Pb, NO3 ions, NO3 minus ions, so we got lead nitrate, that's its formula, and that aqueous, and that gives us Pb2 plus, okay, Pb2 plus aqueous plus 2NO3 minus aqueous. So we see, all right, we broke it up in terms of its ions. But so we got K plus, I negative, and Pb2 plus and 2 nitrate ions. So then we say to ourselves, okay, what happens here in this situation is the partner of K plus is I negative, and the partner of lead is nitrate. Isn't it so? Right, so, but what happens here? We find that the cations change their partners. So when the cation changes its partner, it takes the partner of lead, and lead takes the partner of potassium ion. So if we look at here, what's our products? So our product, I'll just use this color, our product. What's our product? We find and we look at our product. So our product is going to be KNO3, and the other product would be PbI2. Isn't it so? Now we have to establish which is soluble and which is insoluble. We know that all nitrates are soluble, right? And you can check your guideline or your rules. And what do we know about iodides, right? Or halides? We know that group 1 halides are soluble, but the halides of lead, silver, and mercury are insoluble. So this is insoluble, right? Which means it is going to form a precipitate. Okay, so if you have to write the equation for this, we say, all right, getting back to that, we say Ki aqueous plus PbNO3 aqueous, right? Which gives us KNO3 aqueous plus PbI2 is insoluble, so we write it as solid. And as you can see, it forms a yellow precipitate here, right there. So that gives us a yellow precipitate. Okay, so there we've got the molecular equation for it. Okay, but if we look at it and we say, is this equation balanced? And we say we got 2i, we've only got 1, so we need to balance it. So we balance that particular reaction. It means you got 2Ka, 2K2, so that's not balanced. So here we balance the reaction. So we got 2K on this side, on the right hand side, 2K on the left, 2 iodines on the left and 2 iodines on the right, and then we got 2 nitrates on the right and we got 2 nitrates on the left. So that is our molecular equation, right? So that's our molecular equation. Molecular equation. Right? And like I said, the formation of the precipitate, the fact that an insoluble substance can form in this particular reaction, it drives the reaction in a forward direction, and then this reaction is energetically favorable. So now if we want to have a look at the Ionic equation, right? So we say we've got that in solution, and write a balanced chemical reaction, which we've done here. Okay, and if I write an Ionic equation for it, if we write an Ionic equation for it, we know that we're going to have 2Ki plus aqueous plus 2I negative aqueous. I'm writing it in ionic form. Ionic form, right? You'll see in the next lesson why we write this in ionic form. It's useful because it summarizes what happens in a reaction. And then we got here plus Pb2 plus aqueous plus 2NO3 minus aqueous, right? And that gives me 2K aqueous plus 2NO3 minus aqueous. Okay, I'll just put the other one here, plus PBI2 solid. The PBI2 solid is insoluble, so we cannot write it in terms of its ions, right? So that is given to you in ionic form. Okay. Right, now, how do we test for soluble salts? Say in tap water. Right, now we know tap water, if we look at tap water for instance, if we have tap water, I have tap water here, and this tap water may have a lot of salts. We know tap water does have salts, so it could have KCl, potassium chloride salts in here, isn't it? It could have sodium chloride salts. It could have sodium chloride salts in here. Right. It could even have some sulfates in here. So it could have maybe sodium sulfate in here. Right, and that's all soluble. It could even have some carbonates in here. So it could have maybe sodium carbonate in here. Right. So if you given a beaker and you want to now say, I want to know in this particular tap water, do I have any chlorides in there? Do I have any carbonates in here? Right. Do I have any carbonates in here? Do I have any chlorides in here, or a bromide, or a iodide, or do I have any sulfates in here? So if in order to determine that, you will have to know which substance you need to add in order to determine whether you have these ions. Right. But let's look at this here now. We've got sodium chloride. Right? Here's sodium chloride. We know sodium chloride is soluble. Here we got potassium bromide. We know potassium bromide is soluble. And here we got potassium iodide. These are all soluble salts. So in the tap water, all these are soluble. But we want to know if they do exist in water. In order to know whether we have these salts, we use silver nitrate. Right? We use silver nitrate. The reason we use silver nitrate, because we know that if we add silver nitrate to these particular chlorides, we're going to get insoluble chlorides, right? So when we look at it and we say, okay, and we had examples of insoluble halides, right? So let's say, for instance, now we want to know if for instance, do we have, for instance, a sodium chloride in solution here. All right, so we could say, okay. All right, so let's say we have now here. All right, we want to know, maybe, have we got a chloride in here? So let's say the chloride could be sodium chloride, it could be potassium chloride, it could be magnesium chloride. And we want to know whether we have these chlorides in here. Right. So what do? We say, okay, let's add to this. We add silver nitrate. And silver nitrate is also soluble. Alright, so then we say, okay, I've got sodium chloride in here. Correct. Which means in solution we have Na plus ions, aqueous, plus Cl minus ion, aqueous. To that we add AgNO3, aqueous, and we say, okay, that gives us Ag plus ions plus NO3 minus ions. Okay, these are aqueous. So wherever we have these mixtures and a precipitate can form, then it will form, right? Because that drives that particular reaction. So here, if we have now sodium and its partner is chloride, and nitrate and its partner is AgNO3. So what happens in this particular situation? We say, all right, partners are exchanged, right, in terms of this. That means Ag changes his partner and to Cl minus. Na changes his partner to that. So what's the product that can form here? The product that can form here is NaNO3, right? and AgCl. Right, these are the two products that can form. But we know that NaNO3 is soluble and AgCl is insoluble. Right? And it forms a precipitate, and it drives our the reaction. So if we write now a molecular formula for this, we would say okay, NaCl aqueous plus AgNO3 aqueous. When they react, what do we get? We get NaNO3 aqueous plus we get AgCl, which is a solid. Right, AgCl, which is a solid. And if we look at this reaction, is it balanced? Yes, it is balanced, right? And if you want to now write the ionic form of this here, we can say, okay, the ionic form, Ionic equation for this would be NaCl would be Na plus aqueous plus Cl minus aqueous, okay, plus Ag plus aqueous plus NO3 minus aqueous, which gives us Na plus aqueous plus N plus NO3 minus aqueous plus AgCl solid, which is insoluble, which is insoluble. Right, that would be our ionic equation, and that's our molecular equation for this. Right, and there you have that one. Let's look at now test for soluble sulfates. Okay, so let's say here now in this tap water, let me go back to my other color, which says, okay, I have Na2SO4. We know that this is soluble, right? So now we want to know if there's a sulfate present in tap water. So if we want to know if there's a sulfate present in tap water, we say, all right, what reagent can we use? We say, okay, let's use barium chloride. Right? Reason we use barium chloride is we know barium chloride firstly is soluble, right, in solution, but we know that barium sulfate is insoluble. Isn't that so? So we say, all right, we have that. So we say, okay, Ba let's start with that. We say, okay, Na2 SO4 aqueous plus what do we add to it? BaCl2 aqueous. They both soluble, right? And we want to know what it gives us, right? So here, like I said, they exchange partners. So what's going to happen is we've got now here, which tells us, as you can see here, I've got barium chloride added to sodium sulfate, and what happens? We get this white precipitate, which is barium sulfate, and what else do we have in that reaction? Sodium chloride. Right, they exchange partners. So we then have NaCl in solution plus BaSO4 solid, right? And that gives you an indication there. So if we look at this here now, if we want to balance this reaction, we need to balance it. So to balance that, we got 2 Na, we've got 2Cl on the right and 2 Cls on the left. Our bariums are balanced and everything is balanced. Right, now if we want to now, that's our molecular equation. Molecular equation, okay. But what would our ionic equation be for this? Where we show it in the form of ions. Ionic equation, right? Which would mean we break up sodium sulfate into its ions. So we know Na is plus, but we got 2 of it. So it's 2Na aqueous plus SO4 2 minus aqueous. Charges balanced, so we got 2 Na, so it's 2 positive, and sulfate 2 negative, so that balances, plus Ba 2 plus aqueous plus 2 Cl minus aqueous. Correct. And that gives us 2 Na, since we've got 2 of that, plus aqueous plus 2 Cl minus aqueous plus BaSO4 solid. Right, so that is balanced, right? Yes, that's balanced, right? So here we got this precipitate, and this precipitate here, as you could see, it's a white precipitate. Precipitate. Now let's look at test for carbonates. Okay, if we look at carbonate now, what happens here? We got barium chloride added to sodium carbonate. So let's say we have our tap water again, and in the tap water we got some carbonate, Na2CO3. Right, that's our tap water, and we got some carbonates, but we want to know whether we've got a carbonate. So what do? We add barium chloride to it, as you can see. So we say, okay, barium chloride, BaCl2, and That's aqueous barium chloride, aqueous plus Na2CO3 aqueous, right? And we want to see, right? So here I will do this so we know partners get changed. So that gets changed for this, right? For Na, right? And when that happens, what do we get? We get, as you can see here, NaCl, which then says we get NaCl aqueous, right? Plus we get BaCO3 solid. Right, BaCO3 solid. Right. So that's your molecular equation. So that would be your molecular equation. Molecular equation. Alright, that's your molecular equation. If we have to have now the ionic equation for this, ionic equation, yeah, it would then be Ba2 plus aqueous plus 2Cl minus aqueous, right? Which then, and we got 2 Na plus aqueous plus CO3 2 minus aqueous, right? Which then gives us Na plus aqueous plus Cl minus aqueous plus BaCO3 solid. Okay, there you have that. So then we have that ionic equation, and here you have your precipitate as well, and this is also a white, right? White precipitate. Alright, so you can see barium carbonate is a white precipitate and barium sulfate is a white precipitate. Now the issue is it a carbonate in the tap water or is it a sulfate in the tap water? So how do we differentiate between barium sulfate and barium? How do we differentiate between barium sulfate and barium carbonate? Right. So, if we look at it, we've got, for instance, we have for instance, barium, right? Barium sulfate. We have barium, so we got barium sulfate as our precipitate, and we have barium carbonate as a precipitate. So these are solids, right? Both of these. And we want to know whether it's a carbonate or a sulfate. So what we do then is we say, all right, we take barium sulfate, like that, and we add nitric acid to it. Right, barium sulfate, which is a solid, we add nitric acid to it, and we add nitric acid to it. Okay, so we add nitric acid to it, and then we find that nothing happens. Nothing happens. Right, if we suspect it's a sulfate or a carbonate. But when we take barium carbonate and it's a solid and I add HNO3 to it, okay, what I find is that we then get barium nitrate, okay, which is in aqueous solution. Okay, you can see there's still changing partners there, but then whenever a carbonate reacts with an acid, we know that we get carbon dioxide. So we say plus carbon dioxide, say plus carbon dioxide, and carbon dioxide is a gas, plus H2O. Right, H2O. Okay, so we got barium nitrate, and if we look at this here now, and we say, okay, we got carbon dioxide that's given off, okay, and we got water, okay. So if we look at this now, when nitric acid is added to a carbonate, carbon dioxide is given off. Right. So, is this equation balanced? Let's have a look. We've got, say, we've got carbon dioxide, CO3, and this is barium nitrate, so it's BaNO3. Let's just see. Okay. I'm just double check that. So there's barium carbonate. So here I've got barium nitrate. So let's see this balance, and let's check. So that's 2HNO3, right? So here we got 2 nitrates on the right and 2 nitrates on the left. How many oxygens have we got? We got 2 hydrogens on the left, and we got 2 hydrogens on the right. How many oxygens have we got? We got 2 plus 3, 6. Right, let's just see that. We got we've got 2 two hydrogens on the left and we got two hydrogens on the right. So we got two hydrogens on the right and two hydrogens on the left, right? So we got barium nitrate, so we got two nitrates, that's fine. If we look at carbon, we got one carbon on the left and one carbon on the right. So we got we've got three oxygens, six oxygens, 9 oxygens on the left. So how much have we got here on the right? 3 to the 6 and 2 is 8. Yeah, okay, so the equation is balanced, right? Now, if we want to have a look at, so that equation, let's, if we want to have a look at the Ionic equation, in this situation, which we can, but since it is not a precipitation reaction, I will not do the Ionic equation for this, right? But now, as you can see, when we have a carbonate, we got carbon dioxide given off, and with a sulfate, nothing happens. So when you see carbon dioxide being given off, you know you're dealing with a carbonate. Also, carbon. How do you know the gas is carbon dioxide? When you take carbon dioxide, so say test for carbon dioxide. How do we test for carbon dioxide? We know carbon dioxide changes clear lime water. So CO2, right? If we take clear lime water, that's calcium hydroxide. And what happens? So that's like clear lime water. When CO2 gas is passed through clear lime water, we find that it becomes milky. So the reason it becomes milky is because it forms calcium bicarbonate. Right, so it forms calcium bicarbonate, which is milky, means settling out of solution, and there it becomes milky. Okay, so is it balanced? We've got 6 oxygens on the left hand side, on the right hand side, and we got 2 hydrogens. We've got 2 hydrogens on the left, and we got 2 oxygens, and alright, so here I've just given you an indication. So you got 2 carbons, so that's going to be 2 carbons, right? And it's 4 oxygens and 2 is 6 oxygens. And on the right hand side, we also got 6 oxygens and 2 hydrogens. And then I've got 2 carbons and 2 carbons. Okay, I'm just checking if it's balanced. Right, so there you have that. Okay, now let's look at the exercise. The reactions result in a precipitate, right? All of these. For each reaction, write a molecular equation describing the formation of the precipitate and write a complete ionic equation. Okay, so if we look at this here now, if you want to write a complete molecular equation, so we have AgNO3 aqueous, plus we're mixing it with Na2CO3, okay, aqueous, and we know a precipitate forms, so we're going to have Ag2CO3 solid plus NaNO3 aqueous. So that would be A. And the ionic equation for this would be Ag plus aqueous plus NO3 minus aqueous plus Na plus aqueous, is 2 of it, plus CO3, 2 minus aqueous, okay, and that gives us Ag2CO3 solid plus Na plus aqueous plus NO3 minus aqueous. Right, so let's look at B. Okay, let's look at B. Here we have lead nitrate, so PbNO3, 2 aqueous plus Ki aqueous gives us PbI2, and that's insoluble, plus KNO3 aqueous. Okay. Okay. And I've just realized that I haven't balanced the top equation here. I haven't balanced the top one, so which would mean that would have to be 2Na, so that would be 2Na, and that would be 2NO3, right? And which means this would have to be 2, and then that would have to be 2, right? So you got 2Na, 2Na, 2 sulfates, and you got CO3 on both sides. Okay. All right, so let's look at this one here now. That means that would have to be 2, and that would have to be 2, right? So that's balanced. Your nitrates are balanced, your iodine is balanced, and your lead is balanced. Okay, so that's your molecular one. Let's look at the ionic one. Pb2 plus aqueous plus 2 NO3 minus aqueous plus 2 Ki, right, plus 2I negative gives us PbI2 to the solid, plus it gives us 2K plus aqueous plus 2NO3 minus aqueous. Right, so that's balanced. Right, let's look at the next one. That's barium hydroxide and H2SO4. Okay, so you got barium hydroxide, aqueous plus H2SO4. Okay, that's an acid, aqueous, and we say okay, that gives us BaSO4, which is a solid, plus H2O. Alright, that's a molecular one, and we know that that's a precipitate that will form. Right, and if we look at this and we want the ionic equation for it, ionic equation, the first one is a molecular equation. So that would be Ba2 plus, okay, plus OH minus aqueous, and I showed you that if it's an acid, how we break it down. It gives us H plus, but we got two of the H pluses, right? Aqueous plus SO4 2 minus aqueous, which will then give me BaSO4 the solid plus H2O liquid, right? Okay. Okay, that's BaOH2, so that's going to be 2OH. Just sort that out. That's going to be plus 2OH. Right. So it's 4 hydrogens, that means this is going to be 2H2O, right? Which is 4 plus 2 is 6 oxygens, and 4 plus 2 is 6 oxygens, and then your bariums are, yeah, so the reaction is balanced. Okay, there you have your ionic equation. Let's go to the next one, using the formation of this, using information, the solubility indicate whether the following mixtures will form a precipitate or not. Okay, will it form a precipitate here? So what's the possible products that we will get? Magnesium chloride and ammonium sulfate. We can get ammonium chloride and magnesium sulfate, right? And if we look at this is magnesium sulfate soluble, right? We can go back here and we say, okay, if we come here, right, we look at sulfates. So important exceptions. We've got um, sulfates, strontium, barium, silver, and lead sulfates, they are insoluble, right? Otherwise, the rest are soluble. Okay? So, if you look at this here, we find that, yes, is there a precipitate? No. Right? Precipitate formula, we don't have one. Lead nitrate and potassium chloride, we know that there is a precipitate. Right? And what would a precipitate be? It would be PbCl2. If we look at the next one, barium nitrate and copper sulfate, would we have a precipitate? Yes. And what would the precipitate be? PaSO4. And the next one, sodium carbonate and calcium chloride. What are we going to have? We're going to have calcium carbonate. Yes, it is insoluble, and we have let's check that, and we precipitate, yes or no? Yes. And what's the precipitate? It is calcium carbonate. Right? And then sodium iodide and silver nitrate, yes. Right? And what's the precipitate? AgI. Right, let's just double check this. I just want to double check that calcium carbonate. Right? So if you look at carbonates, all are insoluble. The only ones that are soluble is compounds of ammonia, ammonium, and the alkali metal cations are soluble. Oh, okay. So otherwise all are insoluble. Okay, so we just need to sort that out. Right, which would mean in this case sodium carbonate, right? And okay, sodium carbonate and calcium chloride, we said that precipitate, yes, and that's calcium carbonate. Okay, all right, I thought I made an error there. Right, so calcium carbonate is does form a precipitate. Okay, now let's look at using solubility to predict whether each of the following compounds is soluble or not. Ag2S. If you look at your table, you'll notice that it is insoluble. Right? And then ammonium sulfate. Most of the ammonium compounds are soluble. Okay? Check your guideline table there and you'll see that. Right now, if will there be a precipitate occur when the following solutions are mixed? If so, write a balanced chemical reaction and also write an Ionic equation. Right. So if we look at this here now, we got sodium carbonate, right? So we got sodium, Na2, CO3, aqueous. Let's close that. Plus AgNO3 aqueous. Right? And when we exchange partners and look at the products, then we got Ag2CO3 gives us a solid, plus NaNO3 aqueous. Right. If we have to balance this equation, we got 2 sodiums, so it will have to be 2 there, and then that will have to be 2 there, which is then balanced. And if we look at that, yes, it's balanced. That's our molecular equation. And if you want the ionic equation, it would be 2Na plus, right, plus CO3 2 minus aqueous plus 2Ag plus 2NO3 minus, and that gives us Ag2CO3 solid. So that's your precipitate that forms, and the carbonates of silver are insoluble, plus it gives us 2Na plus aqueous plus NO3 minus aqueous, and that would mean 2 of it. Right. Okay, let's look at the next one. Here we got lead, nitrate, and iron sulfate. So, okay, we got FeSO4, and that's soluble, plus we got PbNO3, and that's soluble. You know, all sulfates are soluble, and when they exchange partners, we get PbSO4, that's, we know it's insoluble, plus Fe2 plus, let's first write it in a molecular form. It gives me FeNO3 2, right, aqueous. Right, so we have that, and if we look at our equations, are they balanced? Yes, they are balanced. So we want the ionic equation, which would mean Fe2 plus SO4 2 minus plus Pb2 plus aqueous plus 2NO3 minus aqueous, which gives me PbSO4, so precipitate, plus Fe2 plus aqueous plus 2 NO3 minus aqueous. Right. Let's just see if it's balanced. Yeah. Yes, it's balanced. Okay, there you have it. See you the next time.